Hello, everyone, and welcome to today's webinar, The New Standard Practice for Covered Geomembrane Testing, brought to you by the International Geosynthetic Society's North American Chapter and the Geosynthetic Materials Association. My name is John Allen. I'm your Vice President-elect for IGS North America, and I will be your moderator today. IGS North America has teamed with GMA to provide these free educational webinars. You should know that the International Geosynthetic Society's mission is to educate the industry about geosynthetics. We do this in several different ways. One example is this webinar that you're attending today. We also provide educational classes to civil engineering professors so that they can introduce geosynthetics into the engineering curriculum at their respective universities, and we help coordinate and host industry conferences. GMA provides engineering support, business development opportunities, educational programming, government relations expertise, and industry recognition. GMA influences specifications and lobbies on behalf of member companies and targets key U.S. states to expand the geosynthetics market. GMA also provides a network to exchange information, solve common problems, and develop mutually beneficial relationships. Before we get started, I'd like to go over a few items so that you know how to participate in today's event. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions box of the control panel. You can send your questions in at any time during the presentation, and Abigail will answer them as the questions come in. The recording of this webinar and a PDF of the PowerPoint will be made available after today's presentation. PDFs of the PowerPoint are only available for IGS North American and GMA members. Certificates of attendance are available through GMA, but must be requested via the contact email. I would like to now introduce our presenter, my good friend, Abigail Gilson-Beck. Abigail has over 18 years of diverse civil engineering experience and is a registered civil engineer in multiple states. She spent the first part of her career as a containment facility designer and then joined TRI in 2012 to focus solely on the implementation and innovation of electrical leak location technologies. She has over 15 years and 170 million square feet of electrical leak location experience. That number right, Abigail? 170 million square feet?
Yeah, it's pretty close to right there. It was kind of hard to keep track of changing companies, but yeah, it's all right.
Okay. Her contribution to the field of electrical leak location includes numerous published technical papers, educational seminars, presentations worldwide, and chairing ASTM's committee for the recent revisions and additions to the ASTM standard guide and practices. Everyone, please welcome Abigail.
Thank you so much for that introduction, John. And I'd really like to thank the IGS for having me here today to talk about this new standard. I'm really excited about this new standard. It's been a really long time coming, and it's very much overdue in this industry. So to kind of give you the context of where this new standard fits in, this is a standard for covered geomembrane testing. The only standard that has ever existed for this type of testing is D7007. It was invented in the 80s. It's been largely unchanged since then. So this new ASTM is an improved alternative to D707 for testing covered geomembranes. It is more stringent. How big of a change is this? Well, it depends on the practitioner. For some, it's not a very big change at all. In fact, there's many practitioners already doing this. They probably don't even know that it has a new number, but it's the stuff that we've all been doing for many years because we know this is what it takes to make the test maximally effective and reviewable to other parties. So like I said, I've been doing this for over a decade. This particular method, now it has a designation, and the only real difference for me is that a lot of the documents that I produced for internal review are now deliverables as part of the report, and that's part of what the making this method transparent is. So all of our internal review documents, they're very much part of what the client sees when they get the results of this report of the test back. So it was actually not my initial intention to create a whole new standard that was going to replace D7007. This method actually came from a sort of conversation / request from a client friend who said, how would you test a facility to make 100% sure that you could find all the leaks and even show that there were no leaks in this facility? So I thought long and hard about it, and I came up with this standard, and I called it Electrical Methods for Eliminating Leaks and Installed Geomembrane. Well, that title was right off the bat rejected by the ASTM committee. They didn't like the insinuation that this was the only method to eliminate the leaks. Maybe they were concerned about the liability. You know, it's a big claim that you're going to eliminate the leaks. So I changed the title to Electrical Methods for Mapping Leaks and Installed Geomembranes, because the mapping is one of the key features that makes this new method different from D7007. So how do you go about creating a standard for eliminating leaks? Well, it takes a lot of experience, and not only that, it also takes a lot of failures. And what I mean by that is there's more and more double-line facilities coming online that require testing. When they leak, it's obvious. You can't hide the leakage. If you miss the leak, you know you've missed the leak. There's a new guide out for the placement of, quote, blind leaks, which is a hole that's intentionally created by the owner or the engineer to make sure that those leaks are going to be able to be found during the surveys. So we all collectively as an industry had to go through a lot of experience with missed leaks and what happened and what can we do to make these leaks able to be detected. So that formed a lot of the new standardization of this new method. And the other thing is that when you did have a failure type scenario where a facility was leaking, a lot of times they had multiple firms try to come and solve the problem. And so a lot of us are given other people's reports to review to tell the client, you know, what was or was not done appropriately. Well, you can follow the ASTM D7007 protocol to a T, still not find leaks, and it's still not apparent to anybody, including the person reviewing the report, what actually happened during the test. So this new method, it really just takes D707, makes sure that it's maximally effective. It forces thorough documentation of all the things that really matter, and it makes it completely transparent for anybody taking part in the project, not just the operator, not just the person out there doing the method. Everybody can review the results of the testing out there. So I actually went through the new ASTM, and I went section by section, point by point in this presentation to tell you guys absolutely everything that's in there from beginning to end. So therefore, I'm starting with definitions. And I'm just highlighting the definitions that were put in there that have never been in an electrical legal location standard before. So the word anomaly is one of them. We use it all the time. Sometimes I wonder if folks know what we're talking about when we say anomaly. So now it has a definition. It's an electrical measurement caused by some aberration in the survey area, which may or may not be an actual leak, usually caused by non-homogeneity or something. One of the new and really important definitions is site response current. So what this is when you apply voltage across the geomembrane in a site, this is the amount of current that results. So you inject, say, 500 volts and you get a response current, 20 milliamps, 0 milliamps. You get some value back of how much current is flowing through that survey circuit. Another definition is survey. We say survey all the time, and it means a lot of things to a lot of different people, but for us, it means when we do an electrical evaluation of the geomembrane. And that goes hand in hand with the survey area. A lot of times we talk about the survey area. This may not be the complete containment facility. For this standard, it's only the part of the facility that was covered by material during the test. So if you have a soil-covered geomembrane, it's only the area of the geomembrane where the soil is actually placed. So this is the organization of the ASTM. It provides a summary of the method, the survey area requirements, then it goes on to survey procedures. This is where the meat of the test really is. And then there's an optional section on documenting the zero leak condition. So as I mentioned before, this was originally written as, let's eliminate the leaks and let's document that there's zero leaks in there. But now it's a much more generalized standard. And the zero leak condition is one option in this generalized standard. And the last section is reporting, what exactly has to come out from the report output. So starting with the first section, summary of ELL methods. You have a voltage differential imposed across the geomembrane, and the current flows through leaks. Those leak locations will appear with a characteristic shape on the electrical map caused by the current flow. The shape is going to depend on what method you're applying. All electrical methods have the same physics. The electricity is going to travel the same way. It's just the way that it's measured that's going to be different with the different techniques. So different measurement probes are going to be used for different conditions, water versus soil versus, say, a deeply filled lagoon. Measurements are typically made in a grid pattern. See, it doesn't say measurements should be made, it just says they're typically made, because for dipole and monopole methods, they are made in a grid pattern, but it doesn't say you can't do other patterns depending on what method you're using. These measurements are used to create electrical maps of the survey area, and it should show a characteristic shape that is indicative of a leak so that you know what to look for throughout that electrical map. Method sensitivity depends primarily on survey area conditions. One intent of the standard is to document the zero leak, and it does say that multiple surveys may be required if leaks are found on the initial survey. Electricity flows the path of least resistance. Sometimes if you have large holes in a facility, it'll go there and nowhere else. So it recognizes the fact that you may have to do a second survey if you want to document a zero leak condition. If damage is extensive to the liner or the site is not properly prepared, the method will not work. This is another thing that makes it different from D707. D707 is a box checking standard where you can apply the method no matter what, whether it's working or not. It allows you to apply it and just state the results. But not this method. It's very obvious when it's not working, and it shows, because the last thing we want to do is have a client pay for a survey and not get what they pay for. So at least we want them to be able to know that as part of the results. So the site response current. One thing it mentions is that it's site specific. So a 20 milliamp current draw with 500 applied volts at one site might mean no holes, and it might mean 2 holes at another site. So it's very site specific. So the takeaways from this summary is that you can actually use any electrical method with this, as long as it works, as long as you can document that the leak signature is characteristic, obvious, and you can find other anomalies that look like the artificial or actual leak elsewhere in the survey area. So as long as it works. So why did I want to write it this way? Because there are electrical methods that I don't even know that works just as well as the methods I know, which is the dipole. And I also don't want to prevent future innovation. It's all electricity, it all travels the same, it's just the way we measure it that's a little bit different. The upfront focus is on site preparation. So like I said, it's the same for all electrical methods. It acknowledges that leaks in the lining system can affect the method sensitivity. And like I said, multiple surveys may be required. So this is a leak finding standard, not a box checking standard. Let's talk about the survey area requirements. You need sufficiently electrically conductive material over the geomembrane, no frozen material, and you can add water to the geomembrane. Let me stop on that for a second. What I mean by that is if you have a bare liner and you want to test it, and you want to make sure that you're going to find all those leaks, what this suggests is that a covered survey is better than a bare liner survey. So let me explain that. Actually, I'll go back to a conversation I recently had with a friend of mine, and he said, I have a pond. It's a bare liner. What's the best bare liner testing method to perform on this pond? And I said, well, the water-based, like water puddle method works better on the floor because there could be wrinkles. It works better on wrinkles. And our testing method works better on slopes. And he said, well, what about just filling it with water? And I said, actually, yeah, filling it with water is even better than those because it forces the leak to leak. If you're doing arc testing and you have a hole on a wrinkle, not likely to pick it up. Bare liner testing is very operator dependent, and the leak has to have intimate contact. It has to be close enough for the arc to go through or for water to get through the hole during testing. So the second point is isolation of the cover material from the material under the geomembrane. So the method goes on to explain isolation trenches, geomembrane flaps, things like that help to achieve that isolation between the cover material and whatever's underneath it. Conductive penetrations need to be isolated from that cover material. The point is that when you apply electricity to the cover material, it must go through leaks and only leaks. So you also need sufficiently electrically conductive material below. Subgrade is always moist enough. GCL can be moist enough with adequate moisture. There are conductive geosynthetic products these days you can use. It also discusses double-line facilities. If they do only have drainage net or geocomposite in the leak detection system, you can fill that with water. You can use a conductive back geomembrane as a primary or some type of conductive geotextile type product. Also, the surface of the cover material must have adequate moisture for the dipole probes to get good measurements. You can't let the surface dry out. And it also must have adequate moisture above the geomembrane. If we want to make sure we're going to find all the leaks in this facility, it has to actually leak so that we can get a moist path through the leaks. So it suggests that you should saturate the material to the point that water goes all the way to the top of the geomembrane. You can get a little bit of hydraulic head across that geomembrane. Great. That's going to force a leak path. And when that leak path is covered with material, it tends to stay very moist. We have a question in the question box. Why is it called arc testing, not spark testing? So spark testing is specifically for conductive back geomembrane products. Arc testing refers to when you're testing any geomembrane and you're grounded to the underlying conductive material. Looks like we have, I can't read. Okay, no, I got it. Just that one question. So that's the difference. So most of the sites that I survey are not completely compliant with the goal or the ideal of this standard. And this is part of our everyday life. I live on the East Coast. It's very wet here. This photo that you see is an isolation trench at a tie-in. This is what our isolation trenches look like. This is just a part of life. It rains the day before the survey, which is great because we know our landfill is leaking, but our isolation trench is a little bit compromised. This is fine as long as we document it. We know that this is going to influence our test. We know, or it should show up on the voltage map. If it doesn't, there's something wrong. But as long as it's documented, as long as we still investigate, we can still apply this standard. So, most sites aren't going to be totally compliant, but the difference is that we have to document it. This shows an isolation trench. This type of non-compliance is not acceptable. So part of the standard is making observations about all of the compromised isolation issues and mitigating them before the test. You want to make this test maximally sensitive. When you have something like an isolation trench filled with water, you have to pump. You can do a quick functionality test, see if it works, even if it's there. If it truly is impossible to remove this liquid, you might have to do the test anyway, but this becomes part of your testing results because this is a huge factor in how well the test works or whether it's going to work. So now this is not new. So remember I said we started with D707, we made it maximally effective. D707 details all of the site prep, but it also says, do this if practical, in quotes. I mean, it literally says, prep it this way if it's practical. It's never practical. You never build a landfill with isolation trenches. And folks are going to fixate on this if practical every time and not prepare it the way it should be and have a survey that's less effective than sometimes it needs to be. So you can still do this method if you don't have compliance. You just need to document it. Also, you need to make sure that the test is still functional. And I'm going to give you some examples of that in a couple slides. The other difference between this and D707 is that D707 forces an increase in measurement density. So it says if site conditions are poor, if it's hard to see a leak, just increase your measurement density. Take more measurements. So this drastically increases survey time, thus cost. And in my experience, when I've had a site issue and I've tightened up my measurement density to help counteract that, it literally never has worked for me. So yeah, it's a little bit easier to see a hole when you're a little bit closer. We all know that. But when site conditions are poor, you can measure every square inch and not see a hole. I've had a site that had extensive damage. It actually had a perfectly clean isolation trench, but extensive damage everywhere. And I could be right on top of a hole, touching it, and not sense it at all. Because the current has to at least be contained somewhat in the facility. If not, it just pours out like a sieve, and you can't measure a discrete location where it's exiting. So D8265 suggests that you fix your site first for sensitivity improvement, not messing around with measurement density. So I'm just going to go through each point of the survey procedure, starting with the equipment. The measurement approach shouldn't be electrically or chemically reactive with the cover material. What happens is when they're reactive, you get a voltage difference, and that will affect the precision of your measurements. You also want a high internal resistance of a voltmeter if you are in fact using a voltmeter to measure, which in the dipole method you do. The measurement apparatus itself, dipole, cannot allow a short circuit of measured current. I always thought this was pretty much obvious as far as equipment goes, but a lot of the equipment out there is homemade, and people don't fully understand that, all measurement apparatuses are not all the same. I've had a well-made dipole sitting side by side with a very poorly made dipole. The well-made one measured 10 times more voltage because the poorly made one was not electrically isolative, so it was getting short-circuiting through the legs. So if most of the current is traveling through the legs, you can't get a real precise measurement of voltage right at the points where you're trying to inspect. You must have good contact between the current injector and the return with the cover material and underlying layer respectively. So what do I mean by that? Well, usually it's a metallic current injector. Let's say our cover material is sand. If you just stick it in the dry sand, you won't get any current coming out of that electrode. You have to make it wet. You have to encase it in clay or something to create good contact. Otherwise, your test results are invalid. If current could never get to the survey area, you're not going to have a good test. So the actual leak size isn't as much of a factor as the contact of the leak with the cover material. So this new ASTM suggests basically the same size leak as D707, simply because it's a practical choice. It's the one everybody has in their toolkit. 6.4 millimeter artificial leak says you can go half that if you want, but it suggests the size, but it doesn't mandate what size you use. You just have to report, as part of the report, you have to say what size you did use. So moving on to the procedures, first thing you do when you set up your functionality test is you dig a test pit in the survey area. You're looking for how much moisture is on top of that geomembrane. So we talked about how important that is to make sure that the geomembrane is leaking. Well, usually what we do is we just take a photo. We have to put our artificial leak on top of the geomembrane anyway. So when we dig that hole, we photo document it. Is it wet? Is it dry? What does it look like? We're also recording the response, the site response current all the time with a slide voltage. We do it at the beginning. We do it when our artificial leak's plugged in. We do it throughout the day. We do it at the end. Why do we do that? We want to know how much the survey area is changing throughout the day. Is the cover material getting dry? Did the current go down when we dug up our leak? How much? It's also just a simple check to make sure that the survey was proceeding throughout the day. If you look and all of a sudden your output current is 0, your generator might have died on you. So it's creating that constant check to make sure everything is still working. So the functionality test part is pretty simple compared to D707. We're making electrical measurements right on our artificial leak, and we're making the measurements in the best case and the worst case position. So we know best case, if we land right on the leak, what are the values that we're going to get? Or if we're at worst case, like we're as far away from that leak as we ever are going to be in the survey area, what does that signal look like? And we just want to make sure that we can read that artificial leak no matter where we are. So this is what I'm talking about digging the hole and observing the top of the geomembrane when we're placing that artificial leak. You'll notice that there's a piece of mud, basically like a ball of mud that we kind of smear on the artificial leak because they're metal electrodes. They don't always make good contact with the cover material, so we want to make sure that they have good contact. So this is the functionality figure as part of the ASTM. We have an artificial leak placed on top of the geomembrane and covered. And then we have our proposed grid spacing for our electrical measurements. And so we have one measurement point right at the artificial leak, and we have measurement point 1 and 2 at the worst case scenario. So the measurement grid for our test is going to straddle this artificial leak. So the worst case scenario would be, I'll just refer to a dipole because that's what I use, would be when the front foot is on this measurement point 1, and then the back foot is on measurement point 2. Best case scenario is the front foot directly on the artificial leak and the back foot directly on the artificial leak. So you come up with this table of front foot directly over the AL, back foot directly over the AL, and then front foot on MP1, back foot on MP2. So what are we looking for? Well, when the front foot right on the artificial leak, you should have a very strong negative. When the back foot is on it, you should have a very strong positive. Now you should still have this negative positive shift on measurement point 1 and 2. Sometimes you don't quite get a negative to positive. You might just get a lower value and a higher value. But you still want to see that MP1 is lower than MP2, because what that tells you is that that leak is still detectable at the worst case position. So moving on, the method functionality is determined by those measurements that I just talked about, and it requires evaluation before proceeding with the survey. Now, some people might feel uncomfortable at this point because they're like, well, there's no real criteria. Like D707 says my signal to noise ratio needs to be 3:1. Well, this is where it puts it up to the practitioner to know whether or not that artificial leak is going to show up nicely on the map. Usually, if you can see that negative positive, it will almost always, well, it's 99% of the time it'll show up really well on that map. So those measurements are used in tandem with the site response current measurements to determine how well a survey is working. This does require expertise. There's no recipe for it because every site is different. So I'm going to go through a couple of examples with you from my experience. But every site is different. When you survey a site and you figure it out, you're an expert on that site. You take that knowledge, you go to the next site, you're a newbie on that next site. You take the information, now you're an expert on that next site. Every site is different. So there's no recipe. There's just really just applying expertise and experience. So another thing that's very different about this new standard is that it quantifies whether or not the artificial leak is going to have an effect on sensitivity. And I know from experience that if the artificial leak draws a lot of current, like a significant amount of current, it will have an effect on survey area sensitivity. So I put that boundary as 10%. If the site response current with the artificial leak is less than 10% greater than without it, then it may be connected. So if it only influences it by 10%, that's fine, or less than 10%, it's okay. If the current draw for the artificial leak is greater than 10%, you must leave it disconnected during the survey, and then you create a separate map of it plugged in later. So it acknowledges that even an artificial leak as small as an eighth of an inch in diameter can affect method sensitivity if left connected. It's rare, but it happens. I've seen it. And so this standard creates a method for that. So let me go through this. This is a very common site example. This is a table of voltage and site response current. So I'm applying 500 volts in every case. When I got there in the morning, measured the current draw, 110 milliamps. Plug in my quarter-inch artificial leak, it doesn't change. This is very common. Sometimes it only changes by milliamps, a lot of times not at all. You still don't know whether or not it's working. This doesn't give you all the information. This is one piece of the puzzle. In fact, let me go to the next. This was just a part of the final report for my test I did, so you can see that I have site response current throughout the day. So this is a site it was in winter, around Christmas time. And so during the day, the material would be thawed and we had more current draw. In the morning, it would be frozen and we'd have less current draw. What that's telling you is that I'm constantly checking and make sure that my applied voltage is there. So moving on to the example where I don't have any measurable change when my artificial leak is either plugged in or not. So both of these tables were from sites where that was the case. This on top here, front foot directly over the AL, I have a nice negative. My back foot's on the AL, I have a nice positive. I know that the survey is working. I move to a worst case position and I get a positive followed by another positive. This is not ideal. This is very much less than ideal. I would much rather have a negative value here and a positive value here, but I can still see that this one is lower than this one. So I still know that it's going to show up on the map, and I have confidence that when I'm right on top of the leak, I'll be able to find it. So this in tandem with let me go back to this slide here. So these measurements of applied voltage and current in tandem with these tells me, yes, I can go ahead with the survey. Let's look at this table down here. So this is directly over the artificial leak. I have negative 0.5. My back foot directly over the leak, I have negative 0.25. The good news is that this is slightly lower than this. The bad news is that this is not positive. So automatically I know there's a problem. So I move away from the artificial leak. I make the same measurements on MP1 and 2, and it's the same. Okay, this is bad news. This means that even if I'm right on top of a leak, I'm not going to see it because there's no difference between being on top of that leak and being anywhere else in the survey area. So this is where you stop. You tell your client, this is not going to work. We need to isolate the survey area better, or this test is not going to happen. So there's case A where you're allowed to leave the artificial leak in, case B where you're not. So we're going to figure out how to calculate that. So this is a site where I applied 250 volts and I get 59 milliamps. Then I plug in my quarter-inch artificial leak and I get 61 milliamps. So let's do that calculation. So it's 61 minus 59, the difference, divided by the initial. So it's a 3.4% increase. It's less than 10%, so that means we can leave the artificial leak plugged in during the survey, and that's case A. In fact, let me go back up to that site response current log. This is a site where I knew I was allowed to leave it in, but I didn't want to leave the quarter inch. It's a pretty big hole, so I actually left the eighth of an inch artificial leak in and it actually drew less current than the 1/4 inch. So the next example is we have 300 applied volts, and we're measuring 29 milliamps originally. We plug in our 1/4 inch artificial leak, and we get 41 milliamps. So that results 41 minus 22 divided by 41, 29% increase. That is not okay. That's greater than 10, so we cannot leave the AL plugged in during the survey. Let me go back up to the site response current log. If you notice, this says site response current injector in original position. The next one is current injector in new position. See how the milliamps change depending on how wet that electrode is, or if you could put it in a wet area of the facility or a dry area, that output current will change. So just so you know. Also, it has after excavation of the leaks, it went down by 5 milliamps. That's very typical when you have significant leaks in an area for that to go down. So that's just another one of those data points that kind of control the quality of the whole survey. So following the survey procedures, you take electrical measurements organized into an electrical map of the survey area with the tick marks to show data acquisition locations. If the dipole method is used, you also must survey parallel to every edge, because with the dipole method, you have to travel before and after a leak to see it. And when you survey an area, you're always going in one direction back and forth. So you have to make at least 2 more passes perpendicular to the direction of the survey on the edges that you were always approaching and traveling away from. So the required maps for case A are if the artificial leak is left in during the survey. So we have the entire survey area. So you should be able to see the current injector and the artificial leak. And then the second map is the area around the current injector after you move the current injector to a new location. The third map is the area around the artificial leak with it disconnected. So that area around the artificial leak on the original survey is not valid because it shows the artificial leak. You also need to unplug it and survey around it, make sure there's no leaks that happen to be by sheer chance in the vicinity of the artificial leak. So case B is where you do the entire survey area with the artificial leak unplugged. So again, you need to map the area around the original location of the current injector, because if a leak is too close to the current injector, you won't see it. It'll go right to that leak, and it'll be very, very hard to see. So the third map is the area on and around the artificial leak with it connected. So we're going to show examples of those maps next. There's also a fourth map that's required for the zero leak condition, and we'll talk about that later. So this is a case A map. So this is a map where the artificial leak didn't pull enough current for it to matter, so we left it in during the survey. I can tell you that see this little triangle? This is the low end of the survey, and this was completely flooded with water during the test. So it's very common to see contour lines like this kind of jump up to a flooded area. So let me just teach you real quick how to read one of these maps. This is a map created by Dipole Survey. So this is the current injector in the middle. What it does is it creates a polarity of the survey area with negative on top, positive on the bottom. So I'm color coding this so that you can see a very sharp transition between positive and negative values, because that's what's important to me for reading this. So the positive is green, transitioning to yellow and then white. The negative is red, going to blue, and then black. So the current injector creates positive on the bottom, negative on the top, and leak locations are the exact opposite. They have their little circular peaks of negative and then positive. This one is, there's so many contour lines it's hard to see, but that's a positive peak right there. It's a little easier to see this leak right here See the circle of negative on the bottom separated by closely spaced contours and the positive peak on the top. So there's almost always some anomalies in the area because the cover material is hardly ever perfectly homogeneous. You will see leachate pipes. You will see any areas of ponding water. Sometimes puddles of waters will give you anomalies. This whole sump area was basically standing water during this test. Anything where it's standing water in one area and fairly dry in another is going to look different. So all of these anomalies that show up, they should be addressed. So they need to be investigated. There are anomalies that aren't leaks. In this case, they were like puddles of water. They still need to be pointed out and addressed. You can also see the little tick marks that show the survey area so that you know that the survey area was completely inspected. So things to look for on these maps. Do the tick marks completely cover the survey area? Is the signal produced by the artificial leak well defined and recognizable? Is the current injector visible? Can the influence of the current injector be seen throughout the survey area? Is there anything that looks strange or erratic or like a leak signal that's not addressed, that's not noted as being a location for investigation? Does the mapping match what is known about the survey area? So for example, this line right here showed exactly where there were standing water. You can also see, as I said, LCRS trenches show up. So if it doesn't look like the conditions were during the test, there might be something wrong. Discontinuities. If the generator shuts off and the power shuts off, there will be an abrupt change in the voltage that you see on the map. So you're looking to make sure that it makes sense, that you have a constant flow from the current injector throughout the survey area, unless there's some reason, like a hole, standing water, something like that. Note the contour interval. This should be a benchmark for all mapping. So whatever the contour interval was used, say, see the artificial leak, you want to reference that and make sure that all of the subsequent maps are at least as small as that. So the next map would be the current injector location. So we move the current injector and then we survey below it. Note the contour interval. This is the voltage map of the artificial leak area. Again, same contour interval. You see how you're looking for evenly placed contours, nothing that looks like a leak. See how these contours are on a diagonal? Because that's from this site where, see these diagonal contours? That's what it looks like in the normal voltage field because it happened to be located on an area that transitioned from wet to dry. It's also the angle between where the current injector is and where the AL was. So you want to make sure the AL is visible on the map. You want even contours on those maps unless there's a leak or something else that's strange that's going on. And you want to check the contour interval. So this is a case B mapping example. So the artificial leak is not left connected during the survey. This is our current injector location. Leaks can be discernible, not just the magnitude of the value, but the shape. So see this butterfly shape right there? That's a leak. This butterfly shape, that's a leak. And this analysis is very dynamic. You want to try large contour intervals, small contour intervals. These leaks happen to be tiny, nice slices, very, very small leaks. This one was a little bit bigger. This one was a little bit bigger, but by looking at the pattern, not just the magnitude, you can see the smallest of damage that you otherwise wouldn't really notice. This site had some isolation issues. So each one of these locations, you basically just go and inspect and make sure that the current draw is originating from outside or some current breach. This is the big leak in this survey area right there. Whenever you see the black, that means very close contour lines. So very, very large peaks. But you can still see something like this little leak in here. So again, you're looking for the bubbles, negative below the positive, and this one as well. This is the map of the CI. This one's kind of funny because this anomaly is the opposite of a leak signature. A leak signature would have a negative on the bottom and the positive on the top. This has a slightly positive on the bottom and negative on the top. Why is that? Because there's a little piece of clay that I use to ensure contact between the electrode and the cover material. Sometimes those lumps of clay react with the gravel. It doesn't act like a leak. It actually reacts with the opposite of a leak. So it's actually accepting electrons from the gravel for whatever reason, just different mineralogies. This is what an artificial leak looks like when you have a very strong current draw with the artificial leak. It always looks very, very strong. Again, notice the contour interval. It's 0.2 on the artificial leak map, but the other maps that were created are 0.1. So I said, remember, it should be equal to or less than the artificial leak contour. So things to look for on case B. The artificial leak should be shown clearly on artificial leak map, should be very strong. The contour interval for the main map should be less than or equal to the AL map. There should be even contours on the CI map unless leaks are present or there's some other reason for the anomaly. If the CI is not visible on the main map, an additional map is required. This happens very, very rarely, but when there's no leaks in a survey area, you won't be able to see the CI. Why is that? Because when there's literally no leaks in the survey area and the perimeter is perfectly clean, there's nowhere for the current to go. You're putting voltage in the cover material, you're grounded to the underlying layer, and it doesn't travel anywhere. If you don't have any current travel, you won't see the CI because the dipole measures the gradient. It only measures if the current is traveling somewhere. So we'll talk about this in the next section about zero leaks. Going back to survey performance procedures, after you do all the mapping, you review all of the anomalies, you create a list of anomalies in order from the largest to the smallest signal. When you do your investigation, you go to the strongest signal first. You pinpoint it, you uncover it. Why are we doing that? Because electricity follows the path of least resistance. If you remove the biggest hole from your survey circuit, all the electricity that was going into that hole can't go in there anymore. It will find the next biggest hole to go in. So number 2 on the list is the next biggest hole. Go to anomaly number 2, dig it up, isolate it, remove that from the circuit. By the time you get down your list to anomaly number 14, if that's a hole, it will show up much more strongly than it did on the original map. It'll be much easier to find it. If it wasn't a hole and it was just an anomaly, it won't be any stronger. And that's another way to verify that you're getting every single leak in that survey area. So you want to make sure to record your site response current during this whole event. Before, during, after isolation of leaks. And if the zero leak condition is desired and the leaks were found during the survey, a resurvey may be necessary depending on the survey results. So there are some sites, especially if they don't have cover material that's extremely conductive, and you can find every hole big and small because the current, it can't travel very easily through that material, so it gets distributed better. But it's just one of those things that requires expertise. So let's talk about the zero leak condition. This is the documentation that can show that there are no leaks present in the survey area. How do you know for 100%? Well, the survey area has to be wet. If you don't allow the facility to leak, you can't say for sure whether there's a leak there or not. I know through painful experiences that if a site is too dry, you won't detect leaks. Even largish leaks like a puncture or 1-inch puncture. Sometimes if you have material that's bridging, or say you have a dry geocomposite on top of that, the leak's not in the circuit, it's not going to show up electrically. So it has to be wet. But if you do have good site conditions, you know that the geomembrane is wet on top, you know that there's hydraulic head, you have perfect isolation, you can be 100% sure that there are no leaks, because if there's no current flow, there's no leaks. So the electrical map of a survey area without leaks is night and day different from a survey area with even just one little tiny leak, for example, the artificial leak. So what will happen is if there truly are zero leaks, the site response current will be very, very low, maybe even immeasurable. It'll appear to be zero. This depends on the geomembrane material, but for something like HDPE, for example, 60 or 80 mil, it'll be very close to zero. The CI will not be visible because there's no current flowing off of it. The site response current with AL connected will be a significant increase from when it was disconnected. And you will need a fourth map. The fourth map is a map of the current injector with the artificial leak in. Why do we need that? Well, this is a map of a survey area with no leaks or no detectable leaks. Maybe it was too dry, or maybe there was no leak. But there is a current injector in the survey area, but you don't see it. Well, how do you know if there was just not some bad electrical connection somewhere? If there's some bad electrical connection, it's also going to look like this. There's basically zero volts that are measured anywhere on this map. See how small the contour interval is? And oftentimes when the voltage is very, very low, you see these stripes in the data. What are those stripes? Well, instruments always have some little tiny bit of bias. Say the bias is like 0.001 volts, like it reads that offset. So depending on which direction you're traveling, or if the angle of your dipole is slightly off every time you walk from one side to the other, it will just have a little bit of a difference, but not much. So this is the map of the artificial leak for that site. Extremely strong. Contour interval 0.01. This is the map of the CI when the artificial leak is connected. So this, you see a positive on the bottom and a negative on the top, so it's the opposite of our leak, right? So let's move on to reporting. Are there any questions so far about the procedures? I don't see any questions in the question bar. Okay, so as part of reporting, you need to report any site conditions that don't conform to the survey area requirements. Any locations of poor isolation, dry materials, etc. A log of site response current for the different conditions. The functionality test electrical measurements that we went over. The condition directly above the geomembrane, your test pit where the artificial leak was placed. The measurement density that was used, dipole measurement spacing if applicable, type and size of leaks found, and all of the required electrical maps. So, engineer involvement. Hopefully there are a bunch of engineers tuned in today. This is the most important test that's performed as part of a containment facility construction project. Please, I encourage you to be involved. In general, there's a whole spectrum of engineer involvement. And it's rare for the engineer to be really involved, but you should be. So start with good specifications. Ask an EL survey company if you need help with that. Make sure that a qualified company is hired. Also think about how you want to deal with repairs. So for example, I've had some engineers that were really involved wanting mapping of like post-repair mapping. So when we do this procedure, this test, we isolate the hole, we make sure there's no hole around it, but we don't survey after they repair it, for example. We just provide the maps that you saw there. If you want to have a post-repair map, you need to say that as part of your specifications. Also, I strongly encourage you to be there the first day of the testing. During the functionality testing, you should be there. So if there's any issues with site, with functionality, or site prep, you get it. That is the time to address it, not after the fact. When I do testing on site, I will show my voltage map to anybody on site who will come and look at my computer. You know, it's all about the voltage map. That shows the quality of the test. If the map is ugly, I want the engineer to know. If the map is beautiful, I want the engineer to know. And most of the time, they don't know until they get the final report back. And by then, it's too late. So if you have any issues with what happened during the test, you really need to be there during the test, or at least available, you know, via phone or something, to address any testing issues. Because this is just one of those tests that you want to get 100% right. You want to do it right the first time. You want to find your leaks. You don't want to, especially for double-line facilities, you don't want to find out a few weeks later that something was missed. So my conclusions are, I mean, a lot of this is my feeling based on scientific evidence and my 16 plus years experience doing this. D82 is technically superior to pretty much any previous standards, in my opinion. It provides an unprecedented level of transparency. There's no other method that requires this electrical map so that engineers can see in one glance exactly what happened throughout the testing area. It's also more practical. D707 has a lot of messing around with the measurement density after mobilizing to site. So how do you price a project if you don't know what the measurement density is? It has a really big factor on the price. It's impossible to fake positive. I said it's practically impossible, but it's impossible to fake positive test results for a survey. And any mistakes, issues, or omissions are painfully obvious in the final report. So this makes, you know, everybody do their job a little bit better when you know that it's all going to come out in the wash. So if no leaks are found during the testing process, D8265 is orchestrated to make it known what happened during the test that could cause either poor site sensitivity, or maybe there truly were no leaks, and it can quantify that there's no leaks and this is why we think there's no leaks. But everything before now has been very nebulous, and the report output for D707 is really not reviewable by anybody. It states whether or not there were leaks found and where, and that's basically it. So now we do have tools for documenting a zero leak condition, and it's my feeling that D707, you know, should be replaced by this standard. At a very minimum, you know, this standard should be seen as a much improved alternative. So with that, I hope that we have a few questions from the audience.
There's one that just popped up here, Abigail.
Is it the ARC testing one? I already addressed that one.
No, it's another one. It says, do you suggest a method to measure the electrical conductivity of the cover material? If the site is not conductive enough, is it just based on the leak location technician opinion?
That's a really good question. It's a really good question because we all have different tools in our toolbox. And if somebody comes to a site and says it's not conductive enough, specifically the cover material. It's very easy to water. I mean, it's relatively easy to water. If that wasn't conductive enough, you can always just add water. But, you know, when you hire an ELO survey company, you put a lot of trust in them to know what they're doing and to get this test right. And it's very hard. Honestly, I really appreciate more and more as I know more about it, how hard it really is. When you have easy sites, anybody can do it. When you get to those hard sites, it really is challenging. So, you know, as far as one company saying it's not conductive enough, I wouldn't really say it's conclusive. I think that, you know, they would have to qualify that with, this is what we did to determine that that's not conductive enough. and I would send those results to a second opinion for sure. But yeah, for cover material, it's pretty easy to wet it to get that conductive enough. If you have something like an encapsulated GCL where you can't wet it because it's after the fact, that's one of those things. If one company says it's not conductive enough, I would have them explain exactly how they come to that conclusion and have those results reviewed by at least one other person who does this a lot.
All right. Following up on this same question, what about brine ponds?
So, my understanding of brine ponds, and I've had some experience, that most of the issues with testing has to do with how people are trying to measure inside of the solution, because that's why I have a point in here of saying, let me go back to this point. This standard is very pithy, but very meaningful. And you take each sentence in the procedures or the site prep actually has a lot of implications. So let me go to the equipment. Okay. So see the survey procedures equipment, measurement probes, not chemically or electrically reactive with cover material. If you try to take two stainless steel probes, which are commonly used to do dipole surveys, and you try to measure voltage in a brine solution, you will measure in excess of 1 volt without even any current injected into that, because the steel is reacting with the solution. So, I don't have the solution for every type of liquid out there, but different liquids are going to react to different materials differently. So you need to use a measurement probe that's not reactive with that liquid. So that's the first thing. I think that's one of the biggest issues with surveying and the high conductivity. The other issue is that it's so conductive that if you have even one location that keeps the material from being isolated, let's say one conductive penetration or one outlet that's full, all of the current will go in that because it's so highly conductive. So it's very, very sensitive to the isolation requirement part of the site preparation. Otherwise, the brine solution, it shouldn't be any different from surveying any other facility. You apply the same thing to it. You use measurement probes, not chemically reactive. You make sure it's well isolated, and it should be fine.
Okay. I think our next question, someone's trying to get out of having to walk their whole site. So the question is if you have 0 amps on your power source, like 0.000 amps, you still have to walk the whole, even if you know there are no leaks.
Oh, that's a great question. So I wrote a paper on site response current. In fact, you should have my email contact. I can send it to you. But the whole point of when we first started coming up with the idea of this standard, I'm going to my contact information here, is that we wanted something called a quick test. What is the quick test? That doesn't have my email on it. Anyway, how can they get my email, John?
We'll get it out to everybody.
Yeah. So
I'll take care
So
of that.
I did a whole study of site response current because I wanted to know, can I just measure the site response current when I introduce voltage and know there's no leak? The short answer is yes, you can. But you still have to go through the exercise of, remember I said that it's a site specific index. You need to make sure that it's correlating to something that makes sense on that site. Because just what if, theoretically, what if it's showing 0 amps because your cover material is completely not conductive? Okay, this is possible. It's actually possible. There's solutions it's not conductive. You know what's not conductive? Rainwater. Completely deionized rainwater. If it doesn't touch anything when it comes to the sky, it will not be conductive. So you might measure 0 amps and there's actually leaks there. So you still need to go, I believe you still need to go through an initial exercise with the site. You get the site response index. You say, okay, at this level of current at this site on this day with these conditions, this is what this means. You might have to do the survey once, but once you get that correlation, then you can come and do this quick test where you drop in your probe and, oh, I know this site. I know what it means. I know how much current an actual hole will draw. It's drawing 0, so I know there's no holes, and that's my quick test.
Okay.
So
Next
hopefully that
question.
answers your question.
I did get your email out to everybody. So next question is, could you please explain why the dipole measures current flowing, no voltage gradient?
The dipole measures the voltage gradient, but what the gradient means is that there's current flow. So think of it like the electrical map is like water elevations, and electricity is water, right? So it's flowing from a high point to a low point. If you're measuring the gradient, and if there's a gradient, that means there's water flow or current flow in our case. If you're measuring, an uphill, that means it's flowing. If you're measuring 0, that means it's not flowing. So it's sort of everything is all different pieces of the same puzzle. Yes, you're measuring a voltage gradient. Yes, you're also measuring current flow. Yes, you're measuring voltage differential, which tells you which direction the current is flowing. Does that make sense?
Makes sense to me. Next question. If you're working on a covered membrane, do you excavate the covered material no matter how thick that cover material is to repair each leak? Or what's the maximum that you're...
Oh, what's the maximum thickness?
Yeah.
Yeah, so the previous ASTM D707, it stated that the maximum depth is 3 meters, which is really just, a wet finger in the air. The thickness is actually related to the spacing of your dipole. If you have a larger dipole with more spacing, you can measure deeper, if that makes sense. Like you want to keep your cover material as thin as possible, but if it's thicker, you want to measure with a larger dipole. I put, for this ASTM, I believe I have a 1 meter, like a suggested maximum of 1 meter or 3 feet, because I know that this method works spectacularly well on anything that's a meter or less. Once you start getting thicker, it's harder to see those holes, because the further away you get, the harder it is to see them. So I put a tighter limit on the cover material, because I know in practice, cover materials for something like a landfill, they're hardly ever more than 3 feet deep. And I want to make sure that we can find all the holes. So I don't want to say it's okay to put like 10 or 15 feet of material, but every site's different. And I've been surprised in the past at how easy it is to see a leak through 10 feet of material if conditions are right and you have a big dipole. Anything beyond 10 feet or 3 meters, you just lose too much resolution.
Okay. I've got several questions here that I'm going to kind of lump together related around ones. I have permeable cover for a hazardous waste site. What method do I use on the edges of the site, and how do I do that? I've got a 20-acre closed landfill with a leak. What is an appropriate method?
So
in general, all these questions are related. And I've got another one about who pays for the leak location? Is it the owner, the contractor? What's the best way to specify the different methods for the different applications?
Okay, there was like 10 questions.
It is 10 questions, but I kind of know the answer, and I know you know the answer.
So I guess just trying to start addressing the first questions that came in. What method you use? If the geomembrane is covered, this is the method to use. There was another question in there about the edge, and if you mean the edge that's not covered, like say you have covered geomembrane and exposed in another section, you'd have to use one of the exposed methods for the other part. Most likely it would be the arc testing method, because the arc testing works very well in tandem with the dipole, because it's difficult to use the water-based methods on these like, for example, the isolation trenches or the slopes above the fill material. You can't use the water method there because it'll just trickle onto the soil and ground out. So the arc testing method is a great barrel liner testing method in tandem with the dipole. Who pays for the surveys? Ultimately, the owner. So it's usually part of the project specifications for new construction. Unless the owner knows they have a problem and they know there's a leak out there, then they will contract directly with the leak location consultant to do the leak location. But yeah, usually it's part of a project and the contractor hires the leak location.
But when you write the spec, Abigail, you're going to include all those methods and if you're the engineer specifying and writing the document, you're going to include all the methods and then leave it up to the leak location technician or company to make the best decisions on the situation.
That would be a perfect world, John. I would love it if they did that, because you know what that does is it leaves it up to the contractors to pull out of the toolbox of their expertise to what they feel would be best, because they're the most expert on what's going to work the best. I see too many specifications where the engineer specifies an ASTM or, specifies something that isn't really appropriate for that project. And I don't know if it's because maybe some practitioner who only likes a certain method has somehow convinced the engineer to do that. I mean, I'm guilty of that as well. I'll tell all engineers to use 8265, but I have scientific reasons for doing that. Other people might have other reasons for doing that. But yeah, ideally the engineers, it would be great if they left it up to the practitioner. But I think that's a little more that pertains a little bit more to the bare liner methods, because the bare liner methods are all equivalent. They all work very, very well. But they all have these niches that they're good for. Like one is good for this scenario I just described. The other one is much better for like surveying large areas quickly, for example. So I guess with all specifications, the engineer has to be minimally educated about what they're asking for, which is why these types of education events are so crucial, because just like everything else as part of these construction projects, the engineer is hired as an expert and they really need to know at least something about what they're building. So, so yeah, I mean, they can educate themselves well enough to be able to specify a method, or they can try to leave it up to the contractor.
Okay. If a geomembrane is underlain by a GCL that isn't sufficiently hydrated to be conductive, would that be easy to see?
Yeah, I mean, for this method makes it obvious. I mean, with something like D707, you can hide that information very easily. The GCL is not, you can still get the artificial leak depending on how it's connected. You still get it to like work and make it seem like it's working. Or you can just go to the ASTM says if you can't get a good signal, just use this measurement density and just do the survey anyway. So it allows the test to happen. It allows the test to happen without the GCL conductivity even coming into question. So that's one of the biggest problems with D707.
Here's a great question. On the contour map, is it able, can you get the resolution to show two holes that are close to each other?
Yeah. So whenever you have a cluster of holes, it becomes more difficult, right? But because we're looking at, let's call it a 3D map, because it's like X, Y, and Z would be like our voltage, you can see the shape. So when I'm looking at these maps, I know from the shape whether it's a cluster of holes or whether it's a single hole. It's very easy to see. It has a very characteristic shape. I've done plenty of surveys with a big hole right next to a little hole, and what you do is you're constantly adjusting the contours, and the big hole will just be like overwhelming. And when you jump the contours, you make the contour interval large, and all you see is that big hole. And then you adjust the contour interval to be smaller and smaller, and then you see that other hole kind of showing up. If it's too close to the big hole, it'll kind of get swallowed by that signal, which is why it's so important to uncover it and check the surrounding area. But yeah, this method of data analysis, it makes it pretty obvious, at least to me, because I've been looking at the data for over 10 years, when it's a single point hole or whether it's a cluster or whether it's some weird shape, like a long, narrow hole will look different than just a single hole, or, you know, a series of holes. They do all have very characteristic shapes.
Okay, we lost our guest from India who stayed up. It's got to be 1 in the morning to watch this.
Oh, poor guy. Oh my gosh.
So I think they went to bed. And now we got a couple questions that are like follow up from earlier answers. So let's see if we can handle these. Coming back to brine ponds, have you seen issues with the electrically conductive liner and the conductivity of the water was so much greater than the conductivity of the liner that the flooded test could not be conducted? Okay. This individual had an issue once where they couldn't test in this scenario without flooding the detection zone sump and inserting a grounding electrode into the leak detection sump, so that they had a really good connection.
Yeah, so you definitely have to have a connection to under the liner. I'm not sure if I understand the first part, something about relative conductivity. I can tell you that, like, so you should really read this paper that I wrote a couple of years ago about the site response current, because it's really illustrative of something like, you know, the site response current, which is ultimately, if you have too high of a site response current, for example, you have current just going through the intact geomembrane too much, you won't be able to do the survey. I think that's the scenario that the gentleman or the woman was referring to, where sometimes if you have really, really conductive material, say above and below the geomembrane, and has very, very intimate contact, it will allow the current to more successfully get through an intact liner. So yeah, all of these things matter when it comes to testing, and your practitioner really needs to understand how it all fits together kind of as a puzzle, because something like hyperconductive under and over layer would make a survey difficult, perhaps impossible.
Okay, and then this is coming back to our thickness question. It looks like the individual's got 5 meters of depth down to the liner, and they're wondering if they could increase the separation of the dipole legs and get some kind of detection at that depth.
Yeah, I would think so. I haven't worked on 5 meters, so I can't say for sure, but I would think so. I mean, I would try a 5-meter dipole. It's hard. Once you get beyond a 3-meter dipole, it becomes kind of hard physically, and to keep it all together as one structure. But you could probably still do that with a 3-meter dipole, but you certainly just want to use an artificial leak properly installed to be able to gauge how successful or not it's going to be on that cover material. That's really just the ultimate test.
Okay. We've got some other individuals that are calling in after hours too from the UK, where their electrical leak location surveys are required for basal liners, but not caps. Is it effective or recommended for caps for difficulties in isolation, subgrade infrastructures, and then the flammable gas issues?
So is the question like, is it okay for them to not survey the cap if they've surveyed the base liner?
Yeah. Would you recommend that you survey a cap, or is it even safe?
Yeah, you can absolutely survey the caps. I've done a few caps. It's not wildly popular because I think that folks think that it's, even if there is a hole, it's not going to leak much because there's not a lot of head. But it's just, so it's not wildly popular, but I'm getting more and more requests for that, and it's certainly possible. All you need to do is that perimeter isolation trench. And again, if this is a new construction project, you could always weld some kind of flap or something at the base, or design it so that you have a run out of the anchor trench or something. There are ways to achieve that isolation without too much trouble, if it's a new construction project. If not, if it's an older cap, you're going to have to dig that trench. That becomes an issue. I mean, whether I think it's necessary to do caps or not, I mean, really just depends on how confident you want to be that you're not going to get any rainfall into that system, and also how confident you are in the baseliner. You know, people say, oh, well, if leak location was done in the baseliner, that's fine. Well, I don't know what was done in the baseliner. I've been around for enough years to see surveys done horribly wrong, even when they're trying to be in conformance with the ASTM, because the ASTM D707 is so poorly written. So if a good survey were done on the baseliner with confidence, like using the methods that we talked about today, I would feel more comfortable with not surveying the cap, because you know the baseliner's intact.
Okay. Going back to writing specs, what can the designer do in the design phase to increase the success of a survey over a covered membrane?
Oh, so much. So as part of the specifications, you really need to explicitly say that it's the contractor's responsibility to create site conditions conducive to testing and explicitly lay out these isolation trenches. I mean, you wouldn't believe how many landfills they throw in ELO spec as part of the project documents, and then they don't give you the isolation trench, and then they call you out to test, and it's just wasted money. And not only put it in the spec, but make sure that it's carried out throughout the project. Once the contractor starts filling in that trench and not leaving that isolation, it's very unlikely he's going to go and dig it back up. And you don't want him digging it back up. He might hit the liner. So, you have to have the isolation in the spec, if nothing else. B, you should have something about adding moisture to the cover material, either during the test or immediately before the test. One specification that a company or an engineering firm in New York uses that I love is that they require there to be the contractor to add enough water to the cover material to result in 1 inch of a hydraulic head right above the liner. So they do the calculation, they make sure if it hasn't rained enough, they have to add that much water to make sure that if there's a leak there, that it's going to leak during the testing event. And then, the other thing you can do is just specify D8265. Even just specifying that new standard and requiring that folks have experience with that is going to weed out a lot of the companies that aren't doing a spectacular job.
Okay.
We have time for about one more question.
Yeah, that's what I was going to say. They keep coming. They keep rolling in. This is awesome.
Yeah, just right. Email me later. All you folks with questions, please email me as much as you want.
I think that's just it. I'd love to keep this going, but let's ask the people who are really digging in here on design questions to just give you a call, Abigail.
Right.
For the best way to get her is 512-263-2101, right?
No, that's the main number. My number is 512-623-0511, and my email abeck@tri-env.com.
Okay, I got one more request, Abigail. This one's from me personally.
Sure.
I think we all need a TikTok video of a leak location survey.
Need a what?
TikTok video of a leak location survey.
Oh, a video of the survey actually happening.
Yeah, but okay, look up TikTok with the kids and see if you can come up with a video for us.
Okay, but watching a survey is a little bit like watching paint dry.
I think you can make it more interesting.
The exciting part is when you actually pinpoint and find the leaks and dig it up. But yeah, I'll see what I can come up with.
Okay, I'm going to say thank you, Abigail. thank you everyone who attended. We still got 95 people on the line, and we have people from India and the UK, and who else knows where else. We'll do it again soon. And I would also like to thank GMA for hosting the platform that we gave this on. Very much appreciated to all.
Thanks for having me, and thank you all for showing up. And I look forward to hear from you all for future questions.